Hello, everyone. I put together another version of sample midterm for your study. This is the first question. The first question is actually very similar to the one in the first version. This time I hope we can get this done quickly. Okay, so for the question will be, there are 2 points of interest. One is a -1 and one is a +1. At -1, when we consider limit from left, which is smaller than -1, we choose the function of 1 plus x. Okay. And then it's direct substitution, which is 1 plus -1, which is going to be equal to 0. And the limit from right will be as x approaching from -1 from larger, and that falls into the second rule, which is x squared. And direct substitution, which is going to be -1 to the part 2 and equals to +1. As you can see, the limit from left of -1 and the limit from the right of -1 are not the same. So the limit when x approaching -1 does not exist. And of course, the reason is that limit from left is not equals to limit from right. All right, so you understand what this is testing you about. At the function value at -1, we will be choosing the rule for x squared. Okay, so that's going to be x squared, and x will be replaced by -1. Okay, so to avoid those other mistakes I mentioned before, yeah. So be sure you take care of these little things. As x approaching 1 from smaller than 1, which is going to be x squared, which is the rule. And that's a direct substitution, which is going to be 1 squared, and that's equals to 1. Approaching 1 from larger than 1, right? And the rule would be 2 minus x. All right. So then it's a direct substitution again. It equals to 2 minus 1 equals to 1. And the limit from left and right are the same. Therefore, the limit when x approaching 1 is equals to 1. And of course, the reason is that the limit from left is equals to the limit from right, right? You also understand which theorem this is testing on us. Okay, so because of that. At 1, when x equals to 1, so we choose this third rule, 2 minus x. So that's going to be 2 minus 1 equals to 1. In the piecewise functions, we have 3 pieces. They're all polynomials: linear, quadratic, linear. So the only points of interest is, -1 and +1. At +1 and -1, these 2 points are points of questions. At -1, it is the limit does not exist, therefore it is not continuous. The point of discontinuity is -1. At a +1, the limit is equals to the value of the function at 1. So it is at a +1, f of x is continuous. By this time, the only point of discontinuity is -1. And next, we're going to give the interval of continuous, right? So the interval, the only question is -1, right? So at a -1, is it right continuous? Is it left continuous, right? So we have the limit as x approaching 1 from larger than 1. So let me copy paste this piece, okay? And the middle part we don't need, right? So we just need it to quote that information, right? You can see as x approaching -1 from larger, the value is equals to f of -1, which is equals to 1. So this means f of x is right continuous at 1. Right continuous at 1. But is it left continuous at 1? Obviously, it is not, right? So we can quote the reason. When x is approaching -1 from smaller than -1, okay, that equals to 0. But the function's value at -1 is 1, right? So we're going to take this one and compare these two, right? This equals to 0. Obviously, these two are not equal. So this is what I meant, right? They're not equal. So f of x is not left continuous. Is not left continuous at -1. So now the interval of continuous for the function continuous, okay? F of x, let's say it this way, f of x is continuous on interval, I would say intervals, right? There are two intervals. One is from -infinity to -1. From left, it is not continuous, right? It's not left continuous. And the other one would be right continuous. Okay, right continuous at -1, so -1 to positive infinity. That's it. Okay, that's all for the first question. Number 2, we look at these limits, right? So we're gonna find limit. So you guys know what if exists, right? Otherwise, if it does not exist, why, right? Explain. The first one would take, well, I'm sorry, this is going to be H, all right? So this limit, right, is a complex fraction situation. So we're going to multiply 1, right? And we cannot apply limit laws because that will cause the denominator equals 0. So we have to manipulate something, algebraically. The common denominator is x plus h squared multiply x squared. So this numerator is going to be the same as the denominator. So we have a constructed 1. Anything times 1 stay the same. So now we're going to proceed, right? And this denominator is going, this factor is going to multiply that piece on top, and the denominator is going to multiply the bottom, okay? And simplify, this makes 1, right? And 1 over x squared reduced with x squared, that makes reduction. So we have simplified the complex fraction. Continue to reduce, okay? Continue to reduce, you can FOIL this, but I'm going to factor instead. I'm going to use a squared minus b squared to factor. okay? You can certainly do FOIL. You can do the FOIL, okay? But I just want to show you a different way. So a squared minus b squared, and that factored form is a plus b times a minus b. We are very familiar with this. And sometimes we do it from left to right, and sometimes we do it right to left, right? So in this case, we're going to do it from left to right. So we have a squared, that's going to be a squared, b squared. Okay, so our b is x plus h. So we're going to factor. Okay, so when we factor this, we got x plus h multiply, okay, x minus x plus h. Okay, so we factor it as such. So after this factoring, we got to simplify it, right? We're gonna remove this, right? Simplify these two brackets. And on this piece is gonna be 2x plus h, right? 2x plus h. On the other piece is gonna be negative h. And this h will take away this h in the bottom. So we got rid of the h. So this way we can apply limit law. So okay, this is -1 and this h is gone. So the -1 we can put it in the front. Then take limit, and this will become a direct substitution, right? Direct substitution, and then we're gonna get h will be substituted by 0. We're close to the end. We have negative 2x on the top. In the bottom, we have x raised to the power of 4. Reducing the x, we get a negative, the extra negative sign is not needed. So it's going to be 2 over x raised to the power of 3. Okay, so that was the first question on this one. The second one, I definitively, tried. I hope you try on your own before you look at the solution. Okay. All right. Of course, we know what we use here. On this one, we cannot directly substitute. And what we do is that we can divide by theta on both top and bottom. Okay, so tangent theta will be divided by theta. So on top and bottom, we divide by theta. And at the so this part, we know it has limit as theta approaching 0. This is 1. And we're going to break up tangent theta to sine theta divided by cosine theta. Okay, like this, cosine theta. So we look at this piece, which has limit, and this piece has limit, which is direct substitution. So each individual piece has limit. Now it's time to use limit law. Okay, so when we apply limit law like this, we say we're going to take limits separately. This is the indicator that we are applying limit law. So then we got the limit on the top equals to 1, right? This limit equals to 1. This limit equals to 1. This limit, we can find it by direct substitution, right? Because the cosine 0 is 1, right? The cosine, so this is cosine 0. Cosine 0 equals to 1. 1 over 1 is 1. So in the end, we get 1/2. Okay. The third one, we encounter a I'm going to take a whole look of the entire number two solutions. Okay, so all of these, so you get to see it. Now let's look at number 3. Okay, number 3 is a question that the limit is questionable. Right? But we need to consider limit from left and right. Okay, when x is approaching -6, because the absolute value issue, right? Of course, we need to be aware of the domain. X approaching -6, but x cannot be -6 because -6 is not in the domain. Okay, so in terms of this piece, x plus 6, it equals to two pieces, which we're going to convert it to a piecewise function. All right, two pieces like this. When if x plus 6 is positive, right? If it is positive, then the absolute value of a positive number is the same as the number. If x plus 6 is negative, then the absolute value of a negative number is opposite. So put a negative sign in front of x plus 6. Okay, we're pretty familiar with this. If you still have questions with that, please talk to me, okay? And then go one step further. We have that if we solve this inequality, we will get x greater than -6. And here we're going to get x less than -6. All right. So using this relationship, right? Using this relationship, we're going to take care of this limit situation. Okay. In the limit situation, you can actually handle it in the following way, which you drop the limit to handle it. Okay, some of you like to do that, so I will do it I'll do it this time for you that way. So I'm not going to take limit yet. So I'm just going to work on these two cases. Okay, I'm going to work on these two cases. So these two cases are, right? We have these two cases, but each case, of course, we have that. One case is if x is greater than, right? So I'm going to just copy and paste here, right? If x is greater than -6, right? Then the absolute value of x plus 6 is the same as x plus 6. X plus 6 will just replace the absolute value. Otherwise, the negative x plus 6 will replace the absolute value of x plus 6. You can see that. And we reduce, so right? So now absolute value sign is being dropped. We can reduce it because the top can be factored, right? The top can be factored into 2 times x plus 6, right? So the top is, there's no absolute value, so we can factor the top. By this factoring, right? As you can see, the reduction will be rather, it comes naturally. So this will be 2, and this will be -2. So by this time, taking limit from left and right, right? So if we take limit, x approaching 6 from larger than -6, which is there's a positive sign on the shoulder, the positive sign on the shoulder of -6, right? So this expression, the function the limit is going to be +2. If x is approaching 6 from smaller than -6, right? So we're going to put a negative sign on the shoulder. And the limit of the function will be equals to -2, right? The limit from left. And then you say, well, the limit from left is not equals to the limit from right. Well, right is not it's not the same as the left. I'm sorry. Okay, the limit from right is not the same as the limit from left. Okay. Okay, you can say since. Then we can say this limit does not exist. This is the kind of explanation we expect. Okay, the limit does not exist. When we ask you to explain why, right? We ask you to explain if it does not exist, why? And these are the examples that you can use to, and of course, every limit doesn't exist case has a different reason. But for this particular case, this will be a very good reason to explain because we have quoted the theorems. All right, let's look at question number 3. Question number 3, I selected one of the questions from our homework. Okay, so the proof, once again, right? We need to construct, we squeeze the situation. Okay, so where do we get started? Where do we get started? Once again, we can start from sine pi over x, right? And we should be aware of the domain, x approaching 0 from larger than 0. Because the domain of root x is x greater than or equal to 0, and the domain of sine pi over x, x cannot be 0. So that's why x is approaching 0 from larger than 0 to guarantee the functions involved are meaningful. But this function, also this is true, right? So this is true for the quantity we're considering, right? So this is true for any x, that is not equal to 0, right? So, and of course, it is also true for x is larger than 0. This is true. And then we're going to bring the power into, because this time we're going to bring the power. When we bring the power, how do we know E, we raise to the power, right? It will be, if the inequality is still true. The reason is that E function is an increasing function. E function is an increasing function. So when we write it like this, right, when these exponents is in that relationship, it is still true for the output. So if we can think of these as the input for E. Okay, we think of these as, I put a note here. Note, let me explain. E to the power x is an increasing function, right? We can see that E to the power of x is an increasing function. So by this time, you should be pretty familiar with this function. Okay, E to the power x is an increasing function. I'm going to just put a couple values there, right? Okay, so that's the curve. An increasing function means what? Increasing function is an increasing function. What is the definition of increasing function? Increasing function means, okay, we're going to use these concepts substantially in chapter 4, right? Increasing function says whenever, right? For this, whenever input 1 is less than input 2, then for this particular function, e is increasing, then e raised to the power of x sub 1 will be less than e raised to the power of x sub 2. Okay, so if we see this is x1, x2, x3, then this will continue to be true, right? So if you have less than x sub 3, right, this will continue to be less than e to the power of x sub 3. So you can see this relationship less than, and this is still less than. That's what it means to be an increasing function. And this is the reason for this step. For this step, so the reason is e to the power x is an increasing function. Then you say, what if it's a decreasing function? Very good question. If it's a decreasing function, you have to switch the direction. Okay, you have to switch the direction. Okay, for decreasing function, you have to switch. Okay, so when x1 less than x2 less than x3, you have to change the direction of the inequality. Okay, now we got an increasing function, right? So here you can say because, right, e to the power x. So each step there's a reason. And then we want to multiply root x. Because x is greater than 0, so root x is positive, right? So the next step, we're going to multiply each one, right, with root x. And when we multiply root x, right, we will keep the direction of the inequality sign. So why? Because e to the power x is positive. Okay. So now you say because we must understand these reasons, because root x is positive. Then you say, what if it's negative? If you multiply something negative on every side, you have to switch the direction of inequality. Okay, so these reasons are essential for us to understand, because without these, you can't do it. You can't do it. Okay, for example, for decreasing function, you can't do this, right? For negative number, you can't do this. So now we have created a squeezed situation. Right, so we have created a squeeze situation. So the next, we're going to take the second condition of the squeeze theorem. Okay, so we're going to take limit under the same setting, right? We'll take limit on the same setting. This limit of this piece is going to be 0 because e to the power -1 is a constant, right? And the limit of root x multiply e, right, times e, this is also going to be equal to 0. Okay, so by squeeze theorem, that limit, which is squeezed in between, is 0. Okay, the most important thing is for you to understand each one of the steps and their reasons. Excuse me, and their reasons. Okay, so we're done with these the root function, the squeeze theorem, and we're gonna have 2 other questions on limit at infinity. I pick out these 2 questions because I feel that, these are homework questions, but I feel that I want to give you an optional, a different way to do this limit. We are aware how to handle this, right? The degree for the top is 4, the degree for the bottom is 4. So the reason to find this limit is very straightforward. You just have to divide both the top and bottom by x raised to the power 4, and then apply limit law. Okay, and also apply the other theorem where x raised to the power r, when 1 over x raised to the power r. We're going to use limit law, right? Limit law. And also this limit, right? Limit as x approaching infinity, right? 1 over x raised to the power r is 0 when r is positive, right? So we basically applying these two theorems and limit laws. But I like to mention this technique because if you FOIL this, right, you're gonna get 4 terms here. If you FOIL this, you're gonna get 3 terms times 2 terms, 6 terms. It is not really necessary for us to do that though. Okay, so I'm going to show you a slightly different way. So x raised to the power 4, I'm going to write it as x squared and squared. Okay, so that way I'm going to, the outer square, I'm going to put it under the same squared. And then what? Look at this. X squared divide into 2x squared, and then x squared divide into 1. So we're going to get a 2 plus 1 over x squared. Okay, x squared. So this way you don't need to FOIL. Okay, you don't need to FOIL. So that's what we do on the top. Of course, we cannot apply limit law yet. But let's see what's on the bottom. On the bottom, I'm going to split it to x squared multiply x squared. Okay, 1x squared will give it to this piece, right? So I'm going to split it like this over here. So this x squared is going to move over to this piece of x squared. And this other one, right, I got a square. So I'm going to create another square where we put the square outside. We can put the square outside. And this way, we're going to get a 1 minus 1 over x. So you see, we don't have to do anything like FOIL, right? We don't have to FOIL this. So x squared divided into x squared. So we're going to get 1. So x divided by x squared is 1 over x. Now we have created a situation that we can now apply limit law. Okay, each individual term limit exists. I wish you guys to look at limit law to see the extent of limit law we get to use if we do it this way. Okay, limit law. Okay, limit law, we have adding, subtracting, multiplying, dividing, right? We also have power. So we got to use the power limit law. And we can use the, where's the power limit law? Power. I think, yeah, here, number 6, right? Number 6, we use a power limit law on this piece. Okay, so I'm going to show you. So the next step is that we're going to apply limit law because each individual term has a limit, and the limit of a constant is a constant. So we're going to apply limit law here, limit law here, limit law here, and the limit law all applied. And along the way, of course, we'll use this limit, right? 0. But we also use the power property number 6. Okay, so you can see the extent of limit law we have used. And now in the end, let's see what we got. This is 0. That is 0. and that is 0. So the final limit, right, the top is 4, the bottom is 1 squared times 1, right? So it's 1. So finally the limit is 4. I thought this takes much less work, and it's not necessary to do those other foils, really. Okay, at least that's what I think. But if you do foil, there's not a problem. You can do foil, but you're going to draw the same conclusion. Okay, you're going to draw the same conclusion. Okay, the second limit we're looking at here, this is also from your homework, is that when x is approaching negative infinity, this piece, of course, approaching positive infinity, this piece approaching negative infinity. So positive infinity subtract, adding a negative infinity doesn't equal to 0. Of course, we know we cannot do that. We cannot take limits separately because we have a limit subtract limit situation, right? So how do we handle that kind of situation? Of course, conjugate in this case, right? So we're going to, the conjugate of this term is minus 2x, right? So we created 1, all right? And then we keep going. Numerator times numerator, right? Conjugates. So we're going to get this piece squared minus 2x squared. All right? Continue. So this, we know all the properties involved, right? And so this is going to be 4x squared. 4x squared. I'm sorry, it should be 4. Hold on, I'm coming back. 4x squared. After we got the 4x squared, then we can reduce it. So now the question has changed into, So this is just going to be 3x, right? This is just going to be 3x. So the bottom, this piece approaching positive infinity, 1x approaching negative infinity, 2x is approaching negative infinity. So negative infinity, positive infinity minus negative infinity. So the bottom is going to be approaching infinity. The top is approaching negative infinity. But we still cannot substitute, right? We cannot do limit law, so we still have to do one more step. And this one more step, of course, will be dividing by x. Okay, so this piece divided by x, and that piece is divided by x. And of course, we know that this is just 3, and this is just 2. But because x is approaching negative infinity, right, so we can assume x is less than 0. And in this case, and of course, we understand that the root of x squared equals to negative x, or i.e., that x is equal to negative of root x squared. So in here, we're going to substitute x by negative root x squared. That's why. Okay. And next, what do we do? Right? So we get a focus point, right? So we get a negative sign here. So let's move it to the front. And we can put these in under the same square root. Same square root. So the top is 4x squared plus 3. The bottom is an x squared. Oh, sorry, x squared. So x squared go into 4x squared, we get 4, and the other one we get 3 over x, right? So this is going to be 4 plus 3 over x. So finally, we can apply limit law. Okay? Because each individual constant have limit, 3 over x has a limit. So the next step is going to be taking limits, right? Also, we have applied that property, okay, that theorem, all right? So the limit will be taking individually. The limit of a constant is a constant, so we don't have to show it. And the next step, right, applying this theorem, right? So this is going to be plus 0, plus 0. So in the end, what do we get? We get 3 on top, 3 on the top. The bottom is -2 minus 2, so it's -4, right? So in the end, it's a -3/4. Right? Along the way, we have experienced the infinity subtract infinity, infinity divide by infinity, right? So now we understand that no, it's not equals to 0, it's not equals to 1, right? Similar discussions could apply, but we did that in the previous video, so I'm not going to mention this again or repeat it too much time, maybe it gets you bored. Okay. Once again, in this question, we need to identify the interval. We need to identify the interval and the function. Which one do we identify first? Of course, it's the function first. But this function has a special feature because the domain of this equation. So I'm going to do some think out aloud. Because the situation of in this particular function. For this equation to be true, right? The big domain is x has to be greater than 0. So you cannot choose negative numbers. You cannot choose negative numbers. Okay. So there's at least one root. So then you can say if this is true, right? If there is an x, if there's an x, right? Such that this piece is true, then we got some clue to construct the function, right? So you can move everything to one side. So we can have ln(x) plus 2x minus 3 equals 0 because, if this is true, then this is true, right? So this will give us the clue to construct the function. So let the function be, right, f of x. We're going to choose this piece as our function. Okay, so you can say let this be our function. Don't attack the 0. We talked about it before, right? All right. And then interval. Okay. Because we want it to be equal to 0, right? So we're gonna make sure that 1 is, equals to negative, 1 is positive, right? So let's pick some numbers. When we pick the numbers, we need to be careful because we cannot pick any number that's equal to 0 or less than 0. It has to be larger than 0. So let's pick 1 then. Pick 1, right? When we pick 1, ln 1 is 0. 2 times 1 is 2. So this is going to be negative. Okay. What else do I pick? This time I'm going to pick, if I'm going to say, I can pick E. Okay, but let's see what happens if I pick E. Right? ln E equals to 1. And plus 2E minus 3. Would this be positive? Think about that E is 2.7, and so this for sure is positive. right? So we have found one is making negative, one is making positive. So that also means that we can quote the corollary. So f of 1 equals to multiply 1 of e is less than 0, right? So you can say by the corollary of intermediate value theorem, okay, there exists a C, okay, where would this C be, right? So it looks like we can go on. But this has been on the scratch paper, right? This is supposed to be on scratch paper. It looks like we can continue now. So at this point, you may like just stop to start writing your formal, okay, your formal proof, okay. But the interval is going to be 1, comma e. All right, so let's continue to write our proof. Okay, of course, some of these parts can be used, right? So I'm going to write proof. So first, we're going to let our function be this. Okay? And then what do we say? Well, f of x is continuous on the closed interval. On this closed interval, you must mention this as 1, comma e. Must be closed. Okay? Every function involved is continuous in the domain, because we have those theorems to guarantee that. So we mentioned that. And then we mentioned the other 3 things that we already did, right? So we mentioned all of these. And then you can say by the corollaries of intermediate value theorem, okay, I'll just cut it because they're repetitive, right? There exists such a C such that, right, f of C equals to 0. F of C, so this we have demonstrated the theorem guarantees that this equals to 0. Such C exists. Okay, such C exists. Then we just elaborate a little bit, right? Because this is true, right? If this is true, then we can say ln C equals to 3 minus 2C is true. And then C, the IE, you can say C is, C is, C is a solution to the equation. And what equation is that? So we're going to relate to what was given to us, this equation. Okay, and also then you want to mention the conclusion, right? So you're going to say that this piece has at least one solution. We already find one, right? Once we find one, we have demonstrated there has at least one solution, because another one could be found too, right? Could be found too. But of course, we're not required to find the next one, right? So it's just the wording. Once we know one, we know there's at least one. Number 6, okay, this question, to find the derivative of function, okay, to find a derivative function by definition, I have chosen a one with roots, right? And the first, let's find out, assuming everything is in the domain, right? So let's see what's the domain of this function. Okay, so what's the domain? Domain would have to be 1 minus x has to be larger than 0. It cannot be equal to 0 because it's in the denominator. Therefore, the domain would be x, okay, less than 1. X is less than 1. That's the domain. So everything we do will be in that domain. So let's construct, right? Let's construct the definition. We can do it. F of x we know, right? So what is f of x plus h? X plus h. Everything x will be replaced by x plus h. So for convenience, we're going to just write it as, right, root 1 minus x minus h. All right? Then plug in f of x plus h, subtracting f of x divided by h. Complex fraction, right? So we're going to have to simplify it. The common denominator will be this root, multiply the other root. You could combine these two, but for now, just write it separately, okay? Because this will be more convenient for us for future use, okay? And next, we're going to take these pieces, right? Numerator, multiply the numerator. Denominator, multiply the denominator. No parentheses is needed. No parentheses needed. This makes 1. And this piece and that piece makes 1. And obviously, we still cannot do anything, right? So conjugates. The conjugates would be this root subtract the other root. With subtracting, its conjugate will be adding. So plus over numerator is the same as the denominator. So conjugate is created. And next step, right? The denominator, multiply the denominator. Here, you must make sure you insert a parentheses for the sum because we moved it over. And this piece times that piece is going to be a squared minus b squared. So you're going to have a squared minus b squared. Okay? And then what? All right, so this is going to be 1 minus x. And this piece will be just 1 minus x minus h, right, to replace the whole thing. But if you write it this way, you are already making a mistake. Okay, so please insert the parentheses. You can open the parentheses now, right? Because if you open the parentheses, what do we get? 1 minus x minus 1 minus x, that's going to make 0. So we get a plus h. So our next step, right? So this just be a positive h left because it's minus negative h. All right, we're closer to the end. H and h will be reduced, and this one can be omitted. So now we finally can take a limit. Okay, so we finally can take limit. Taking limits, right, as h approaching 0, the whole of this piece, right, and it's just a direct substitution. Really just a direct substitution because it's not going to cause the 0 denominator. So h will be replaced by 0. You can see that it's not necessary to multiply them, make it more complex, right? Just keep it separated clearly. So this piece, you're going to get 2 times of that, right? Over here is root 1 minus x times root 1 minus x. This is going to be just 1 minus x. Okay? There's a 2 here, so we simplify it. We are going to get 1/2. Okay, to bring the 2 to the front. And that can be your answer. Or if you like to use exponents, right? 1 minus x raised to the power of 3/2. That's done. So either one is okay answer. Okay. And question number 7 here, to find tangent line. Hold on, let me give you the whole of 6. Okay, show you the whole of 6. The whole of 6 is here. All right. Number 7. To find the slope, we're going to do derivative, right? So that's our function. So the derivative dy dx equals to, we're taking derivative of root 1 minus 3x. Okay, 0. So we're going to get 1 over 2 times root and differentiating, right? That was a u, right? 1 over 2 times u, and differentiating 1 minus 3x, that's going to give us a -3. So we got a -3 over 2 and the root in the denominator. Okay, and then substituting for slope. Slope of the tangent line passing the point, right? -1, 2, and to the curve of the function that was given. So that slope, we're going to call it m. M would be the derivative of the function evaluated at x equals to -1, which is right here, right? So we're going to replace x by -1. Boom. X replaced by -1. Simplify. What do we get? 1 minus 3 times -1, this is going to be a +4. +4, you take in root is a 2, right? And this is going to be a -3/4. -3/4. Okay? And then the equation of the tangent line, right? The tangent line passing, right? So with all of them specifics, right? So that's going to be y minus y sub 1 equals to m multiply x minus x sub 1. Hold on, this is equal. So the slope is in place. y1 is a 2, x1 is -1. Okay, simplify. We got y equals to -3/4 times x, right? This will become +1, right? So this is going to be, let me write it again, right? This is going to be x plus 1. Sorry about that. X plus 1 plus 2, because I added 2 to the other side. Okay, so this piece, x plus 1 and plus 2. one step further, one step further. So multiply negative 3/4 with x and the negative 3/4 with 1, that's going to be minus that, right? And plus 2. What do we get by these, right? So 2 is 8. Oh, sorry, 8 over 2. 2 is equals to 8 over 4. I'm sorry, 8 over 4, right? So in the end, we got negative 3 over 4 times x plus 5 over 4. 5 over 4. All right. We're making progress. We're making progress. Differentiate number 8. Okay. Number 8. dy dx. Obviously, in this case, we will have to use chain rule, right? So you multiply these product rule. First is product rule, and then chain rule, right? So we differentiate that one, and we differentiate the other one. So this way, you're guaranteed you're not going to miss anything, okay? And then we keep going. We keep going, right? This one unchanged, right? We're going to differentiate that part. So it's going to be chain rule. So it's going to be 4 times x squared plus 1 to the power of 4 minus 1, which is going to be 3. But this is not done. We have to differentiate x squared plus 1. That will give us 2x. And then we multiply that part. Okay? Plus, we keep this part, and we differentiate the other part, right? So it's chain rule again. So 5 times, okay, so 5 times, this will be to the power of 5 minus 1, which is 4. And you also have to differentiate the inside. That will give us 2x plus 1. Okay, by this time, you are pretty much done. But if you want to get maybe some extra point, you probably would like to factor. Okay, factor it out. So I'm going to take the whole thing to see what we can factor out. Okay, what can be factored out? X squared plus 1 to the power 3, and there's x squared plus 1 to the power 4. So if I can take this one out, and this one will take the power 3 taken out, so we only have 1 power. This piece has power 4, and this has power 5, so I'm going to take out power 4. So take this part, power 4 out, and power 5, take 4 out, we get 1. This is 8x, right? And this is a 5. So I'm going to bring the 5 over here. Okay. You could go further, but today I'm a little tired. I think this is fine. Okay, this is fine. The second one we're going to be working with. Okay, so let me show you the whole thing here. Okay. The next one, dy dx. Right, I'm going to put it here. Parentheses is really not needed, but the textbook put it there, so I'm going to put it there. So differentiating, so this is going to be negative sign of the parentheses. Okay, they must be together, and then quotient rule. So we're going to take quotient rule on that piece. And that's going to be the denominator squared. Okay, differentiating the top. Okay, differentiating the top. Keep the bottom. And subtracting, we're going to differentiate. And subtracting here, okay, differentiating this other one. You can change the bracket to parentheses, but I already put the bracket there, so just leave it there. It doesn't hurt anything. Next step. Okay, next step. Differentiating this part will be new. Okay, so we're getting the derivative 1 is 0, so this is going to be e raised to the power of 2x and then multiply 2. Okay, subtracting e to the power 2x. The derivative of e to the power 2x is e to the power 2x times 2. On this part, the same thing, except it's a e to the power 2x, right, times 2. Times 2. Okay. By this time, we can do some factoring. What I meant is that we got a 2 times e to the power 2x, 2 times e to the power 2x, right? So then we're going to factor this out. Factor this out. Oops, sorry, e to the power x times 2. Okay, just leave it like that. Let's not do anything special, right? Take out e to the power 2x times 2, e to the power 2x times 2, so put it, this is e to the power 2x times 2, all right? Inside the parentheses, so this negative sign apply into each term, so there's going to be minus, right? So here is minus 1 plus, right? Minus 1 plus. So these e to the power negative, it's e to the power 2x and the e to the power 2x, they reduced. Make 0. Make 0. Oopsie. So these two are gone. So we got negative 2 inside the bracket. And negative 2 times 2, that's going to be negative 4, right? So negative 4 times negative, that's a positive 4. And last, actually, you could stop here, but I like to bring this one to the front. So that does not cause any confusion, doesn't cause any confusion. If you like to bring this forward over here, that's also okay. It's also a good idea. It's also a good idea. All right. Last one in number 8. We're almost done, okay? I'm a little tired. You can take a break. So I'm just going to get this done. dy dx. Chain rule, obviously, right? So this is going to be 1 over 2 times the root. Okay, then we're going to differentiate all inside the root. Differentiating inside the root, the derivative 1 is 0. So we're going to differentiate just x times e to the power negative 2x. Obviously, that's product rule, right? That's product rule. So when we're going to do product rule, be sure you're going to put a bracket about it. Okay, so now we're differentiating these two, right? So let me write it down. First differentiating x and then differentiating e to the power negative 2x. set up properly. Next, this equals to 1. That's done. And this derivative is going to be chain rule. Okay, so we get e to the power negative 2x times negative 2. Be careful. Don't forget those parentheses unless you want to bring negative 2 to the front. If you put it here and you didn't have the parentheses, then you are making a mistake because it's going to be regarded as this piece subtracting 2. Okay, so the parentheses around the negative 2 is necessary. Simplify. Okay, so I'm going to bring the negative 2 to the front. So this is going to be negative 2x. Factored out the e to the power negative 2x, right? Put it here, and we're done. We're finished. Okay, finished. Number 9. Oops. Number 9. Solving for dy dx. This is an implicit differentiation. Implicit differentiation. So we're going to differentiate on both sides with respect to x. With respect to x, right? So this is going to be dy dx, right? So this we already have a dy dx here. And next, right, we're going to apply chain rule. We're going to apply chain rule. And applying chain rule, of course, this is going to be e to the power of x over y, right? And then differentiating x over y. So basically differentiating x over y. So that's our situation. So it's going to be, well, on the right-hand side, this makes 1 minus dy dx. We're going to dy dx on the other side. What do we do with this derivative? Quotient rule. Okay, so we're going to do the quotient rule, which we're going to get the denominator. This is f, this is a g. So this is going to be y squared. Right, on the top, you're going to have x prime y minus x y prime. Y prime is dy dx. Okay, x prime is 1. 1 times y is this y. Now, we got an interesting situation. We have dy dx here, and we have a dy dx here, right? How do we bring them together? How do we bring them together? So we have to do something to bring them together and solve for it, right? So this will require some algebraic skill. So first we're going to multiply y squared on every side. Okay, we'll multiply y squared, and we multiply a y squared. Okay, so this way the y squared and this y squared will be gone. So we have e to the power of x over y, multiply that piece, and this need to be in parentheses, equals to the other side, which is y squared minus y squared multiplied by dx. Okay, we multiply y squared on both sides. And next, we still haven't get them together, right? So we're going to have to distribute e to the power x over y. Okay, so e to the power of x over y. So this piece is going to multiply, okay, and multiply that. And the right-hand side doesn't change. Now everything is kind of separate it. So we're going to bring dy dx together. Terms without dy dx on the other side. Okay. So bring this term to the left and subtracting this piece. On the right hand side, it was just the y squared, subtracting this term that without dy dx. Now you can see dy dx are together. We're going to factor them. Okay, factored out. So finally, we get dy dx isolated by dividing the parentheses on both sides. Dividing the parentheses, dividing the whole of the parentheses on both sides. We can remove the parentheses. So this is the final answer. This is the final answer. Okay, make sure you practice on this. You can do it yourself. Okay, it's very important. And this is largely not only just implicit differentiation, also there is this algebraic solving equations. Okay, solving equations. So this is the whole of the question, the solution to the whole of the question. All right. All right, last one, logarithm differentiation. Okay, we understand we cannot use the derivative rule for exponential function, and we cannot use it for power rule either. So we have to take logarithm ln y equals to ln of the right hand side. Okay, applying power rule, ln x, right? Ln x is going to be, this is the powers brought to the front, multiply ln of sine x. So this is the multiplication situation. And take derivative on both sides. Okay, with respect to the same variable. So we're using implicit differentiation, where you can call it logarithm differentiation. Okay, on this product. On this product. Okay, on the left hand side, right, we know it's just going to be 1 over y dy dx. Implicit differentiation. On the right hand side is going to be product rule. Okay, so these two, right, differentiating on that part and differentiating on the other part. All right, continue. Continue. The derivative of ln x is 1 over x. And of course, that multiply ln of sine x. Plus, we keep the ln x, right? And differentiating this piece. This is going to be chain rule, right? Ln x, so it's going to be 1 over sine x, and then you differentiate sine x, so it is going to be cosine x. Okay, so organize our terms, dy, so 1 over y dy dx, right? So just copy this piece, equals to, on this side, right? So we're going to have ln of sine x over x plus, on this piece, this is really cotangent x, right? So it's just write ln x multiply cotangent x, no problem. And last but not least, almost the last, right? Multiply y on both sides. So dy dx is equals to y multiply the whole of that. Boom. And last, substituting y I is equal, that was given originally. Right here. There. And that's the end of this so-called the sample midterm. Mainly, you guys can make up your own. So, give you some ideas and practice. If you have any questions, please don't hesitate to reach out to me. Thank you for watching.